Welcome to the fourth video in our series on how to use a computer and the different devices in it. In this video, we are going to discuss how to connect the CPU and memory to a clock device in the computer. In the first part of this series, we talked about how to just use the CPU and the memory. In the second part, we connected that to a disk. In the third video, we connected it to a screen, and now we're going to connect it to a clock. What is a clock? So a clock keeps the time, even when the computer is turned off. It usually uses a battery in order to continue keeping the time. The clock device increases a counter every interval of time. So the clock device has some resolution, for example, every millisecond or every nanosecond, and it increases a counter every tick. Now the counter is usually based on this time here, 1st of January 1970 at 000 UTC. We need some reference point in time that our counter can be based on. And this is called the epoch, and it is quite usual in computer science to and in computer engineering to use this offset. Now, which instructions can we issue to this clock device, or any clock device in general? The first instruction is to get the clock resolution and range. The resolution is how often the clock ticks, for example, every millisecond or every nanosecond. The range is how long the clock will count until it wraps around. The second instruction is to get the current time in seconds for some resolution. Let's look at these two instructions. So the first instruction is to get the clock resolution and range. This function takes a device number. We might have many different devices, clock devices on our computer that have different configurations. Then we pass in two pointers, one pointer to return the resolution and one pointer to return the range. This is an example here of calling it for device number 0. We pass in a pointer and we pass in a range. Now for this old time device up here, we might get a resolution of -4. This means that the clock keeps the time of a granularity of 10 to the power of -4 seconds, which is tenths of a milliseconds. This is a very common resolution for old timers, as it used a quartz crystal to do the counts. The range of this time device here, I don't know. But for a modern computer, a timer device is typically built into the CPU. So a very typical granularity would be -9, and that is 10 to the -9 seconds or a nanosecond. And the range is typically 15 or 10 to the power of 15 seconds. It can even be much more. But that would keep us going for 30,000 years until there's a wraparound. The second instruction is to get the current time. Now again, we pass in the device number and we pass in the resolution that we want. Now, in this example here, we pass in a resolution of -3, which means that we want to get the current time in seconds to millisecond precision. Now I ran this function just before recording this video, and it returned the following value for the number of seconds since 1st of January 1970. Now, given that we have this simple interface towards our clock device, what about time zones and what about date formats? Now, we definitely need a device, a clock device, in order to find the current time. But as long as we have that, we can just use computational libraries in order to compute, for example, a formatted date or time zones. Typically, we would have a database of time zone information, and we would configure into our program which time zone we are currently in. Then we look up the time zone in the database, and summertime and wintertime and stuff like that, and then compute the local time. Now, in order to use this interface here, we need some kind of driver. There are many ways to build this driver. We could, for example, build it using the C standard API, the functionality in time.h. We could build it by directly calling the Linux kernel functions. We could use the x86 instruction called read time specification or timestamp. Or we could use the Windows API functionality. In this video here, we're going to use the Linux kernel directly. So let's look at how to implement the resolution and range function. Here we call the Linux kernel function ClockGetRes, and we specify to the Linux kernel the real-time clock. This function will return a time spec structure that contains two things. It contains seconds and a nanosecond fraction. If this call succeeds, we check that the seconds is 0, because the resolution will probably not be in the matter of seconds. It will probably be some nanosecond resolution. And we check that the nanosecond resolution is above 0, because a resolution of 0 would not make any sense. Now, the resolution is given in some amount of nanoseconds. If, for example, we get 1 back, which is a very typical value, then we know that the resolution is -9, 10 to the power of -9 seconds. So we get 0 here in the second part. But if we get 10 back, for example, then this will evaluate to -8. If we get 100 back, it will evaluate to -7. So we get back which resolution our system clock supports. This is how we get the current time in seconds by calling the Linux kernel. Here we call the Linux kernel ClockGetTime function. We specify again the real-time clock, and we get back a time spec function structure again. Now, if we wanted a resolution of 1 second or higher, for example, a 10-second resolution or a 100-second resolution, then we compute that value here. So if we wanted a 10-second resolution, this would increase by 10 every 10 seconds. Now, a much more typical situation is to ask for a resolution below 1 second. And here we compute the fractional part of the seconds, the nanosecond part, and put it into a double, so that we get the amount of seconds since our offset point. Now, in order to call the Linux kernel directly, we can implement that in assembly as like this. The Linux kernel functions getRes and getTime are number 229 and 228. We put that into our REX register and do a syscall. And here we can see the signatures of these two functions that are available in the Linux kernel. Finally, here is how we can use our driver. Now, this program here mostly only depends on CPU, memory, and a clock device. I've also added a sleep instruction here so that we can run a test program and see how good our timer is. I also added 2 prints in order to see what the different times were. If you run this program, we can see that we get two second values, 1 second apart, and a little bit here below the microsecond level. So here we use only our two functions, the get resolution and range, and then we ask for the current time in seconds for a microsecond precision. Now, of course, these printf functions use the screen, and that is covered in a separate video. So again, this program works on any combination of CPU, memory, and clock device. The only thing we need is a clock driver in order to get the resolution range and the current time for some resolution. Again, this is a simple and powerful abstraction that allows us to use a clock device. In the next video, we're going to cover how to connect a CPU and memory to an audio device, and what the essential instructions for using an audio device are. If you found the contents of this video interesting, then you might want to check out this book. Thank you.